Okay, so I repeat like Kirk that thanks Eliezer for the great introduction, but I really want to thank Eliezer for first. None of you really probably aware that Eliezer initiated this great idea, but much more than initiating, he actually acted completely alone to raise the funds, which is the most crucial part, and then and of course to organize. But the funds were the crucial part. So anyway, so yeah, my talk that can be, so this is, I would like somehow this to be sort of a standard in these schools that we do here. That a first talk is really introductory to some following research talk that is building on the first tutorial talk. So my tutorial is regarding reconstructing trees, phylogenetics, evolution in general, and it is quite different than what have been shown here until now, but I am not sure this is less important, and I will focus on specific, not entire evolution, but some specific part of evolution. And I, like yesterday's talk of Bogdan, I invite you to stop me when something is unclear. I normally tend that my talks will be very, very slow and very, very clear and not covering so much material, at least the tutorial talk. Tomorrow's talk is, you will see, is more advanced. Okay, so what are we talking about? So let's see, any light here? Any? No pointer. Okay. So so evolution informs about everything in biology. Big genome sequencing projects produce more and more data. So what? So what about the more data? So evolutionary history relates all organisms and genes and helps us understand and predict. So interaction between genes, so we can see genes by evolution that they are related by similarity or not similarity. We can see pathways, and the pathways help us understand function, of course. Origin and spread of diseases, this is very important. We will be able to see something of this tomorrow, but if you speak with Eliran, my student that was here, he's pursuing some very specific project about that is related to evolution and even to phylogenetics. Origins and migrations of humans, this could be shown in the first week that was here, talks by John November and a few others, and more. And I always like to cite someone that is an icon in evolution. Maybe Professor Jim Lake that is here happened to interact with him. Tadeusz Dobzhansky, nothing in biology makes sense except in light of evolution. So what is a phylogeny or a phylogenetic tree? So it represents evolutionary history by that form that the leaves normally represent living organisms, okay? And the branches and internal nodes represent extinct species or equivalently evolutionary relationship, okay? Okay, so like I said, so what is the outline of this introductory or tutorial talk? So we start with the basics of supertree construction and explain why it is in a way different than the traditional phylogenetics. We first, we start with the rooted supertree. I think maybe that was, that was mentioned by Eliran, and explain the mean cut versus the max cut. I want to say now here that also this part maybe was not so much here emphasized, but I will speak also about basic algorithms and notions from classical computer science or combinatorics, because this is a very significant part of phylogenetics nowadays. As opposed to all the very heavy stuff, statistics that you guys hear all the time, that is, again, impressive. Okay, so then we move to unrooted supertree, and we speak about the quartet max cut. That is some mechanism or idea that was developed in our lab. And so let's start with supertree reconstruction. So standard phylogenetic reconstruction actually operates in this way. So we take sequences that we believe that are orthologous, meaning that they evolve from a common ancestor, okay, some gene A, that we take from these guys, these organisms, organism 1 to 5, and we infer the evolution of these guys basically, or these sequences, basically or primarily by sequence similarity. However, sometimes we don't have such homologous sequences for all the set of organisms that we analyze. Okay, so this is the case here. For gene A, we have only for these guys, 1, 3, and 5, but for the other organ, but we have gene B that evolved entirely differently, or could evolve entirely differently, and we have this for that set of organisms. Okay, so moreover, data, this is molecular data, but data can come. We have sometimes morphological data, we have other ideas. We want to exploit all these pieces of information and to combine them into one big general hypothesis or theory over the evolution of all our organisms. Okay, so this is the supertree task that aims at combining all these trees, or even in general, all the source of information that we have, to combine it into one big theory of evolution. Okay, so let's see the example here. So we have these 3 pieces of information, and for simplicity, we will focus here mostly or only on trees. Okay, so we have here 3 pieces of information. Let's see how we join it into one big tree. So these guys actually, and I will define precisely the mathematics, they allow us to infer the big tree over the entire set of organisms. Okay, so let's now distinguish between very principal or fundamental distinctions: rooted versus unrooted trees. So in rooted setting, mathematically, we have, this is the rooted setting, we have trees are represented by least common ancestor. This is the relationship. Yes? One slide, okay? This one. Exactly. They are given in supertree. They are given to you seemingly without the supertree gets this as input and says, I don't care how they were inferred. Normally, you know, in big projects, you also reconstruct these guys, okay? And sometimes even you have, for the whole set, you might have the whole sequences, gene A for all your sequences, but for some other considerations, some other, for convenience, you decompose into small sets, you reconstruct very accurate trees, and then you join them. Okay, so the supertree can sometimes be even used for that. Okay, and actually this is very common approach in reconstruction. Okay, so so trees are represented by least common ancestor, LCAs, and the basic reconstruction unit, something that if you take any part from it, it is not anymore informational, is a rooted triplet. And what the rooted triplet says is this, that these two guys, they might not be even more similar to one another, but they just have a common ancestor, the one above, we have nothing. Their common ancestor is a descendant of the entire ancestor of the three guys. This is the only information. They can be very, very far apart. In the rooted setting, trees look like that. And here we don't have ancestry information anymore. Rather, we have splits between the taxa. Let's see what is a split. So the basic reconstruction unit is an unrooted quartet. So this is the quartet, and this is the split. If we take this edge here, we actually disconnect the tree. So every edge in the tree actually is a connection point that if we take, we have two splits. And the quartet, we will see, is the basic reconstruction unit. Let's see precisely. So what is the underlying supertree approach? So given input trees in various sizes, like here, the same example from before. Now we see the mathematics behind it. So decompose the input trees into basic units. So the two guys at the left, the two triplets, are already at basic units, but this guy is decomposed, the rooted quartet is decomposed into 4 triplets, and now we combine the resulted units into a complete tree by satisfying the maximum unit. So we will see what is satisfying, but we want that input to be combined such that into one tree, such that every basic unit is satisfied. And this gives us the tree. This is exactly the underlying, say, mathematical combinatorics from the beginning that gave us this tree. So like I answered that before, this is suitable also for large phylogenetic reconstruction projects, where inference of a single big tree is inaccurate, or sometimes slow or infeasible. And then what we do is to accurately build or not such, but small sets, and then combine them together by supertree, and the supertree is preserving the accuracy of the small trees. So how we actually amalgamate rooted triplets? So it was found by accident that actually a classical algorithm from database theory can serve also here to a specific case is phylogenetics. And look what it does. it works recursively by a divide and conquer approach, okay? Construct, and this is, so what is a divide and conquer? We partition, or we partition our input into one, or we solve one sub-problem here, and that is based on solving underneath smaller problems. Okay, so construct connectivity graph over the set of taxa and partitions them according to the connected components. So let's see. So this is our underlying taxa, okay? Now, and we have this set of triplets, okay? So these triplets, actually what we see, we look at the two guys here and we connect them in the underlying connectivity graph, okay? So we connected them by edge. Okay, so here we have the fish. So we connect the fish, okay, by an edge here. Let's see more. Just a minute. Yeah. So this is the only rule that we have. Let's see now concrete example on number. So this is our input set of triplets, and this is the set of taxa. 1, 2, 3, 4, 5, 6. Okay, so let's go one by a triplet by triplet. So we start with 1, 2, and 3. So construct the connectivity graph, VE as follows. So this is these are the nodes in the graph, okay? Now we go triplet by triplet. We start with 1, 2, 3. Oops, sorry, that was fast. 1, 2, 3, okay. So it should be colored by red, the 1, 2, 3, and we connected 1 and 2. Let's continue. Now we connected 3 and 2 by the second triplet, okay? So, okay. Now 4 and 1, 4, 1, 5. So we connect 4 and 1. Now 1, 3, 4. 1, 3, 4 are connected, you see. And finally 6 and 5. 6 and 5 are red now, okay? So we handled. So this is the divide phase, okay? Now we conquer. What we do? Now we solve, yes, yes.
What do you mean by 1 and 2?
What do you mean 1 and 2?
1 and that the first line was that graph.
Yeah.
On the top.
1 and 2 are, you see, 1 and 2, the triplet, so the triplet is, this is a text, okay, textual, so this is the graphical representative. 1, 2, and who else was there? 3. So I represent it in a text version, okay? So this is 1, 2, 3. This is 2, 3, 6, okay? So this is the divide phase. Now what we do? So now we analyze, look what we do. We, the same graph, introduce a new tree node. So we now build the tree recursively, introduce a tree node. This is a tree node U. It's a new tree node. And now we have two sub-problems. This is a sub-problem of the form we saw already, and this is again a sub-problem. 5, 6, and no triplet. 1, 2, 3, 4, connected component from above, and 2 quartets, 2 triplets. Okay, you see the 2 triplets that relate to these guys. Okay, so we continue. Now no triplet here because no triplet is contained in 5 and 6. Okay, so we continue. So apply the algorithm recursively for every component of G with the triplets that wholly contained in the component. Okay, so we have the 2 components, 5, 6, 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, and now we continue. So and hang the result. This is a recursion. Hang the resulted trees that emerge from below. We hang them under U. Okay? So no triplet here, so we just hang the two guys, 5 and 6. We hang them under a new tree node, U1. And now let's solve this. So, yeah.
So what happened to like 2, 3 given 6 and everything? Did you just delete them?
Whoa. Oh, yeah. Good question. Let me address that. Great question. Let me address that a little bit later.
1 and 2 and 3, doesn't that make a cycle? Why the cycle?
I don't care. I mean, I don't care. I care about connected components. Huh?
Okay.
I don't care. It's not about cycles. It's about connected components. Okay? It's just about connected. The algorithm works. You know, you can compute many things here, maximum flow and whatever you want. But the algorithm is interested only in context.
The output a tree then?
What?
Shouldn't the output in the end be a tree?
The output, of course, is a tree, but I explained to you. So you generate it recursively. You just now partitioned the two sets by, this will be the root of the tree. You will see in the second slide. Okay, now we solve recursively. Same algorithm. 1, 2, 3, and 4 is the underlying nodes. Okay, let's see what are the edges, what are the connected components. So we start with 1, 2 versus 3. So we join 1 and 2. Okay, you see that? Now we look at the next triplet, 2, 3 versus 4. And we connect 2 and 3. So this is one connected component. This is the other connected component. Continue recursively. Now we put here under U, we put U2, U sub 2, okay? This is U2. And we have this connected component just hang below and solve recursively this guy. So this is only one triplet that is represented 1, 2 versus 3, okay? 1, 2 versus 3, and this is under U3. This is U2 that we saw from before. And now we go back. So we hang U2 under U. And this is the tree. Okay? We go up. We fold up in the algorithm. Okay? This is the recursion. You go down and you roll back. So we roll back, and this is the tree that returns from the recursion. You may want to program this and see how nicely it works, okay? This is the final tree. That's it. You so far, I mean, you don't care about just the comp, and it is very classical algorithm, very elegant algorithm from 81, from database theory, very nice. However, life is not so simple. Sometimes, in many cases, the triplets are incompatible. That means there is no tree that resolves all of them, actually, always. I mean, as biologists, we know never. And we have so many, and we will return to it later, tomorrow. Okay, so for instance, if you have these, just build the connected component. Okay, so we have, these are the underlying, this is the underlying graph. I go here. So do it with me. 1 and 2. Let's connect 1 and 2. Now 2 and 3, you see? And now 4 and 2. Okay? One connected component. That is equivalent that and you could work the combinatorics here without this, that these guys will not, the ancestry relationship here will not agree on any tree. Okay, so it's such a simple example. Okay, so this gives rise to the maximum triplet consistency problem. Okay, MTC. Find a tree tip T star that resolves the maximum number of triplets, okay? Okay? And the proposition from 97, MTC is MP hard. And the reduction is quite nice and simple reduction by some constructing some cycle that I might return tomorrow with tough combinatorics that we will show. The reacting is from feedback arc set. Like I said, I will touch here basic notions from combinatorics or algorithms. So feedback arc set, NP hard problem. Okay, Saron, you wanted to? Oh, okay, I saw you. Okay. Okay, so what is the? Okay, so let's see some solution. And I remember I spoke with. The guys, Mike Steele, that is big icon in phylogenetics. And I asked him, hey, what is the idea here about your min cut? And he said, look, the biologists need some, they don't care about NP hardness. They need some solution, okay? So it based, the solution that was suggested is based on the observation that every edge in the connectivity graph, okay, every such edge that we saw represent a triplet. So what can we do? So we run our Aho et al. Algorithm and we get stuck, a connected component. We cannot partition. We cannot just partition it to disconnected connected components and continue. What can be done? So we got stuck. Now, if the connectivity graph is connected, compute a min cut partition, a connected graph, okay, into two parts where the weight or the number of edges for simplicity is the minimum. And continue in the recursive algorithms. Let's see the example. Okay, so actually, why min cut? So recall we had an inconsistent input, okay, a connected graph. I told you it is equivalent. Recall every edge in the connectivity graph represents a triplet. We went triplet by triplet and added edges, correct? So if we partition the graph, or partitioning the graph is equivalent to removing edges. We cut these edges, we violate these triplets. So across edge violates the respected triplet, and therefore min cut. However, something also very important here is that actually min cut, okay, so the problem is NP hard, the problem of all these, but min cut is efficient. And now one may immediately wonder, hey, but if I have an efficient algorithm for the problem, why the problem is NP hard? Let's see the contradiction here, okay? Let's see the contradiction. So what are the shortcomings of the min cut? Why not min cut? Okay, which will answer my question, why, or the contradiction. Okay, so min cut criterion is local. We have some recursion here. We just solve something above, and some connectivity graph. It may may ruin all our global optimality. Oh, this is the input. I mean, by maximum likelihood, maybe things that by some morphology, whatever. The min cut is like indifferent, like doesn't care. But okay, so it is part of the input. So yeah.
So for the min cut, how are your weights decided?
Weight?
Yeah, because it isn't min cut. You want to.
Oh, so it is like I all the time say, it might be a multigraph. So if several triplets, if you have 1, 2, 3, and 1, 2, 5, then 1 and 2 will have 2 edges. Okay? And so, and in your graph, it will be just 1 edge with, 2. Okay? So it only, it counts only violated triplets. Consider the following scenario. Okay? 1, 2, these are the triplets. Okay? This, when I started to think about this, I looked for some pathological example, and I came up with such an example that gives us actually this connected graph. Now, compute mean cut here. So mean cut, what mean cut knows? Mean cut just cuts. So it may, and actually when I played with these guys, I said maybe in reality mean cut will not. Maybe in reality mean cut is, maybe it is okay. So this is the mean cut. It cuts whatever you want. So we cut these guys, and that actually violates that triplet, 1, 2, and 6. Okay? So we cut it. We separated 1 from all the others. Now, another mean cut. So we don't have that triplet. Now another mean cut that removes 3 from the rest. So it violated this guy. Okay? Another mean cut. Oh, great question. So exactly, I mean, I was a student at your stage, PhD student, and I liked combinatorics. So, you want to give some pathological example. I really didn't know that later, when I first played, later in my postdoc, I really gave it more substance, and I saw that mean cut is so bad. I mean, it can be as bad as random tree. We will get to randomness and all this probably tomorrow. Okay, but you're right. So when I played with it, like pathological or toys example, I chose the worst to show. I just wanted to do some game, some combinatorics game. Okay, so I chose the worst example. So this is that, and now, and so what did we get? So we separated 1 initially, we separated 3 afterwards, and we separated 2. And all these guys are later just hang like that. This is also not informative. You have no information here, but you remain without any triplets, so you just hang them here. So this is the mean cut. I think not any triplet here. Actually, yeah, I have here. So this is, okay, so key observation. So we will soon see. So let's see. The key observation is as follows. Someone noted that before from you. Maybe Fahad. At every step, when the algorithm is stuck, some triplet must be violated. You must separate the guys to violate a triplet. But someone asked me, hey, where that triplet disappeared? Why it disappeared? A triplet that disappeared is satisfied. Okay? Okay? And this is the key observation that when I had these games, these small games, as a PhD student, I noted that. For a triplet, ij bar k, denote the original ij edge as bad edge. This is the original or traditional edge of Eho et al. Okay, this is the bad edge. But introduce 2 new good edges. We have some more information in the input. Why disregard it? Ik and jk. So these are the traditional the original bad edges. However, these are the new good edges, okay, that now show or augment the situation with much more information. Now, this is the Q observation. This is the Q observation. Every triplet ij bar k such that ij is not in the cut, but either ik or jk is inside the cut, that triplet is satisfied. Is satisfied. And you will not see it anymore in your recursion because one will be in one side of the connectivity graph and the other two will be in the other side. Okay? You will not see it. It was satisfied. So find a cut that maximizes the ratio between good and bad, because if one is not good and one is not bad, then this triplet is inside some connectivity graph, okay? And it will go down. Decide on it later, okay? Don't just kill it or satisfy it. And this is some distinction. We try to be more global here, not satisfy the most now or violate the least now. So we want to maintain something for, yes?
How do you find the edge 5, 1?
What edge?
5 and 1.
5 and 1. They are not, do I have such an edge? You're right, so there is some, I need to see, very good comment. I need to see, this stands for which triplet? Maybe it is, did I have 5 and 1 are not good in any triplet here. Maybe it should have been 5, 2. I see 5, 2 need to have, okay, 5, 2 need to have, so maybe the 2, so I have also 6 and 1. Okay, so I need to check, I need to repair that graph.
Okay.
I see 6 and 1. Yeah, okay, so it should be 6 and 2. So probably the sum. Okay, so you see the triplet to second to the right, if you put 1 instead of 2 there, you get that. Okay, you see that? So it's some mistake of mine. But you see what I mean? Yeah, between 1 and 6 because they are in the same triplet and they are on the two sides of the bar in that triplet. Okay? Am I still sound okay? Okay, so find the cut that maximizes the ratio. Okay, and this is obviously, again, this is a toy example that I devise myself, that where min cut will be terrible, okay, like you saw, and max cut will just, let's see. Okay, this here, first we must violate, we have a connected graph. So max cut violated one triplet, but in one, I don't know how to, but you know, in shutter, when you have a sword, just killed all the problem, okay? So that's it. You don't even continue down with your recursion, okay? And this is also, in terms of complexity or running time, this is also some advantage, okay? So, where so in the min cut, actually all the triplets, I don't remember, but I think no triplet or only one triplet was satisfied. Anyway, this is the new criterion. We look for a cut, C maximizes the function. That function, there is some problem here that is not seen. I don't know why it is. But anyway, there should have been some function here. Where the sigma? I don't know. Anyway, let's see. Okay, note we will return a cut only if. So it should be, okay, it should be some function here that I don't know why the symbols have disappeared. It's sigma over the good edges minus alpha times the bad edges, okay, where alpha is the ratio between the good and bad edges. But actually this problem, satisfying this problem is equivalent to solving max cut, and max cut again is NP hard. Now I said few times here, NP hard, efficient, and again NP hard. Now listen, even if I solve the max cut efficiently or precisely, it doesn't mean that I solved that problem efficiently. It's just a heuristic. And this is the idea here, that the mean cut was efficient. And here even the heuristic is NP hard. So it's really counterintuitive. And someone needs to be, a student needs to be very persistent to pursue this on his own without, where even a heuristic is NP hard. Anyway, some exact algorithms do exist for max cut. The exact, I mean approximation, but even they are quite slow. Okay, so now we started, when I say we, now I joined my host at Berkeley, and we gave this SDP-like heuristic. SDP, semi-definite programming, okay? So we embed our nodes on the three-dimensional unit sphere, you will see soon, and we move the points over that sphere, so we actually embed a combinatorial setting into a geometric setting, and now we move the points to satisfy a geometric function, okay, that again we just replaced the indicator variable with a distance. This is, yes, that. Yeah. Okay, so the specific function is this. I don't know why, because at home, okay, so it dij minus alpha sigma. Okay, so it's ij is bad. ij is good. Okay, so we now have alpha, and we look for the alpha that will maximize that function, okay? And the d is exactly the distance on this three-dimensional unit sphere, okay?
Quick question. You're not maximizing over the alpha, right? You're maximizing over the d.
Exactly. So alpha is some parameter here.
Okay.
Okay, alpha is a parameter. And I want to find the alpha that will maximize, okay? So this is easy, but to find the alpha is the hard part, is the max cut. Okay, so you need to search for that alpha, okay? Okay. So what we do here, so now this is done by moving the points on that sphere toward the center of mass with respect to its neighbors. This is the internals of the algorithm, and after a constant number of times, we just partition the cat or the sphere by a random hyperplane. So let's see an example that will actually vivid to you or will materialize what we are talking about. So this is our setting. This is our max cat. Let's see how this is translated into geometry. So this is how we mapped the points into that three-dimensional, into the sphere. Okay, so we maximize distances between guys that are connected by good edges. Okay, and we minimize the distance between guys that are connected by bad edges. And now, with high probability, any hyperplane that you will draw here will separate these guys. Just look at it. Any hyperplane, for example, this one will partition the two guys or the two sets. Okay. Now the harder task. So up to here, we dealt with rooted triplets. Now let's now start with less details. So the harder task, how am I in terms of time? Okay, so the harder task is unrooted trees. Inferring unrooted trees is problematic. Triplets are useless in unrooted setting. This is a triplet. You have no information at all here. Okay, the smallest information unit is a quartet tree, unrooted quartet. This is a quartet, and there exists an edge splits that separate 1 and 2 from 3 and 4. Okay, 1 and 2, 3 and 4. So quartet amalgamation. Now this is important, and this is beyond the combinatorics. Quartet amalgamation stands at the heart of almost any phylogenetic task. If you recall from the first week, Ben Raphael was here and spoke about cancer and all the phylogenetics. He actually spoke about quartets. Whether he knew about it or not, you will see that eventually his setting is the same that we deal here. Okay, so from triplets to quartets, no available divide and conquer algorithm. Even this algorithm of Eho and al. Does not help here. This is a hard task in general. We will return to it. Quartets introduce non-trivial obstacles for working with cats. Okay, even the simple task that we have, the connectivity graph, all this does not work here. Now let's see how we combine quartets. We have these two guys. They agree. So we can combine them into this tree. Okay, so 5 is exactly placed here. Yeah. Why we have the light? This is better? No. Oh. Yeah. Okay, so this is 1, 2 versus 3, 4, and this is 2, 3 versus 5 and 4. Okay, so 5 is exactly, this is 5. 1, 2, 3, 4, 5. 5 is here, and this is exactly inferred from here. Let's not, if later you can see that this is really the only case. However, and this is the tree, this is the quintet, we call it. However, sometimes we have 1, 2, 3, 4, and 1, 2, 5, 4. Now it's not so clear where 5 can be. Let's see where we put 5. It can be either here, okay, or here, and actually even here. So we have 3 possibilities that will later will influence on how we solve all the problems. So some overlap and structure is required even when, and this is important, even when all quartets agree on a tree. Okay, so a tree, realizing them exist, finding that tree is hard. This is such a fundamental difference from triplets. Okay, so quartet extension. So we now have the same graph, but we have here the edges. So draw good edges between the rest. Okay, so these are the blue and the reds from before. You remember the reds and the blue? So we have them here. And assign unitary weight here to these guys and alpha, minus alpha to the bad edges. Okay. And a maximum cut here, the same as before, a maximum cut here will strive to put cherries. These are the cherries. Okay, the cherries. We'll have to put them here on one side and the other one on the other side. Okay. So what is the quartet multigraph? So we have two quartets like that, and we join them. This is our connectivity graph or the quartet graph. G of Q can connect by good and bad edges simultaneously two vertices. So you see the vertices here are connected by good and bad edges. Okay? And you have them. So we had to adjust in my last 5 minutes, we have to, I don't want to violate the time and not to lose you. So we had to adjust the recursive algorithm. So this edge violates a triplet, and this edge satisfies the triplets. In quartets, it is much more problematic. A cut, okay, a cut in the graph can violate that triplet. Cut, separate 1 and 3 from 2 and 4, it violates the quartet. Separate 1 and 2 from 3 and 4, this satisfies the quartet. Okay, you see that? Okay. But we have here a complicated case. We only separate 1 from all the rest, and we call it deferred. The destiny of that quartet is not yet solved. It's deferred to lower stages. The challenge is how to cope with these deferred quartets. Now, this is some internals that I don't want to tire you with them, but it's quite a nice technique we found to cope with this. So we introduced some new taxa, and we replaced the name of it. I don't want to go into that too much, but the theorem that if all cuts are found correctly, the correct tree is returned. So again, it's somehow solving an NP-hard problem, but if all cuts are found correctly, and of course the cuts are not found correctly, at least in theory. So we did not solve a NP-hard problem. Okay, and this is the tree. Again, these are the quartets, and we replaced, these are the deferred quartets, 1, 2, and X. Okay, and here 3, 4, 5, 6, and X. Now we have these guys, they are artificial X and Y. And let's not go into any detail here and just show some simulation results. This is how we generate random quartets. Okay. This is the benchmark. Okay, so here we introduce 30% of noise. Here we introduce 10% of noise. We checked quartet max cut with MRP. This is topological accuracy, okay, of QMC versus MRP. Okay, so QMC has substantially lower error rate than MRP, which is the prevailing method for that. However, this is the big difference. Running times in log scale of seconds. This is like 2 days, and this is okay, this is 2 minutes or 4 minutes, something like that. And new algorithm that we developed in 2012 that uses intrinsic and later even weighted max cut that was published recently with Eliran as leading author. And here it allowed us to analyze much bigger data sets, okay? And triplet max cut that is just being published now by other guys in the lab, which is the max cut over the triplets. And let's skip real data so you can go. And theoretical results we will discuss tomorrow that build all the randomness that we developed here and all the ideas of the max cut. We will deal with them tomorrow. It will be quite involved. It is okay. Concluding remarks: Supertree of max cut over min cut and MRP. Superiority of the max cut idea, okay, the max cut idea in triplets, in quartets, significant advancement. This is Cypress was, when I was postdoc, Cypress was a big project. I don't know where it stands now. Open problems, we will discuss all of them tomorrow. I want to acknowledge my collaborators here. So Satish Rao was my host at Berkeley, where we developed the max cut and the triplet max cut, the quartet max cut. Rafi Yuster is from the talk tomorrow, and the students that were involved is Reuven Cohen, who was my postdoc, Nitzan, Daniel, Oren, Eliran that is here, and Gur Sivilia that is in Israel, and this is the funding, and thank you very much.